Okay, so in this video we are going to go through some of the basics of linear algebra for machine learning, right? So we are going to go through the basics. We are going to just have a little bit of introduction, like as in what is linear algebra and how it is useful for machine learning, right? So, what is the importance of machine learning? What is the importance of linear algebra in machine learning? Well, I will introduce you some of the comic of XKCD, which actually uh, describes as in how we are actually doing things in a comical way. So, suppose we your machine learning system is basically a pile of data, and that pile of data, what it does is it goes through a linear algebra, uh, basically a linear algebraic equations, and then on the other side we get the result. So basically that is what linear algebra is doing in machine learning, right? And if the answers are wrong, just we have to change how the data is given to the model, the machine learning model. Like that is the rough analogy of as in how linear algebra is utilized in machine learning, right? So what are the topics we are going to cover in linear algebra for machine learning? So we are going to cover what we'll first understand, like why do we need linear algebra. Then we will go from scalars to tensors. Then we will study the flow of tensors in machine learning. We will then study the matrix operations such as determinant and inverse. And then we will study eigenvalues and eigenvectors. And we are also going to study singular value decomposition and principal components analysis. So we are going to study all this. So what is linear algebra? So linear algebra is basically a branch of mathematics which is basically concerning itself with linear equations. Now, what is a linear equations? The linear equations are equations which look like this, such as ax1, a1x1 plus a2x2 plus and it continues to a and xn, and it results to some value as b. So this is basically the format of a linear equations. Now, in vector notation, we can say that ATX is equal to B. But this is basically a transpose of all these variables, coefficients in a vector format, and it gives out the value as B. So this is called linear transformation of X. This equation basically is what it is saying here is I have given that diagram in here, is that this equation is what it is saying is that basically it is an equation of a plane in a multi-dimensional space. So that is what it is showing basically, right? And the variables itself are basically the points in different dimensions. So that is what this equation is representing in the mathematics in here. So why do we need to know linear algebra? So linear algebra is actually used throughout engineering, because linear algebra is a continuous math rather than discrete math, and computer scientists have a little experience with linear algebra because it is a continuous math. They have more experience with discrete mathematics, right? But however, linear algebra is very essential for understanding ML algorithms. So machine learning algorithms, we do need to know linear algebra. Why do we need to know? Because when we convert the vectors from such as x1 to x1 to outputs by a series of linear transformations, then only we can get a proper meaning of whatever computation we give to the model, right? So that's why we need to know linear algebra. Now here we will discuss concepts of linear algebra needed for machine learning and omit other linear algebraic aspects, like linear algebraic topics of linear algebra basically. So yeah, that is what we are going to do. So in this, what we are going to study, what are scalars, vectors, matrices, and tensors. We will understand how to multiply matrices and vectors. We will understand what is identity and inverse matrices. We will understand linear dependence and span and norms also, and then we will see go through some special kinds of matrices and vectors, and we will then understand eigen decomposition. We will also go through single value decomposition. We will also go through the Moore-Penrose pseudo inverse uh, topic in this linear algebra, and we will also know what is a trace operator. Then we will also then we will understand what is a determinant, such as principal component analysis. So we will understand all these things, right? Now, first we will understand scalar. So this is basically in here. This portion, the first topic, is what is a scalar. So scalar is basically a single number, right? Scalar is a single number, is basically in contrast to objects in linear algebra, which is usually an array of numbers. A scalar is a single number. So a scalar can be a real valued number, such as a fractional value, which is 1.2, 1.3, or 1.4. Or it could be a natural number, right? It could be a natural number, it could be a natural number of units as well. So in here I have given the mathematical notation in here. So what it reads here is that x belongs to R. R here represents the real value numbers, and x basically represents the element which belongs to a set of real value numbers, right? So not a set of real value numbers, but the set of all real value numbers, right? So this is what this equation represents. So this sign basically means belongs to, right? So here it means that x elements belongs to the set which is known as real value numbers. So yeah, a set which contains all the real value numbers, the element is the part of it. And here it is something different. It says that the value the element n belongs to the natural number set, right? So in here it says that there is a set of natural numbers and n belongs to that. So that is what it is saying in here. So usually the scalar number is represented by lowercase italic x. So that is how scalar is represented as. Now let's go to the vector. What is a vector, right? So vector is basically an array of numbers arranged in order, right? That is basically a vector. Each number in the vector is identified as an index, such as it is an ordered index. It has an ordered index. So every element has a index value, right? So this is a vector. So it has the index value such as 1, 2, and it goes on till n. So usually the vector is written with bold case such as x, and this is how it represents. So one thing to understand in here is that every element in this is actually another dimension. So if you understand what are dimensions, so dimensions is basically a paper is basically 2 dimensions. It has height and breadth, but a cube has 3 dimensions. It's a height, breadth, and depth, or height. Yeah. So yeah, height, breadth, and depth. So that is 3 dimensions a cube has. So length, breadth, and height is cube. Length and breadth is basically plane. So that is basically that is basically a dimension, and a line only has 1 dimension, which is length. So yeah, that is what dimensions are. I did say something my tongue did slipped a bit. So I said that height, breadth, and depth it's for a cube, but it should be length, breadth, and height, right? So these are the three dimensions of cube. So that is what we have to understand in here. So in here, for example, in this vector here, each variable is another dimension in here. So this vector has n number of dimensions. So in here it says that if each element is in R, so if each element is in R is basically um, real value, basically a real valued number in certain dimension, then x is in Rn. So it says that the x, which is any number x, is basically in Rn. So Rn is basically the total number of dimensions in here. So that is what it is saying. Like if each element is in R, then x is in Rn. So the x value is basically is in Rn. So this is in Rn. We can think of vectors as points in a space. So as I have explained in here, so that we can think of vectors as a point in a space. So it can be so it can be a certain point in a multi-dimensional space. So we can think of vector as like that, right? So we can so suppose if you are talking about coordinates in a plane such as x and y, that is a vector with 2 dimensions, right? And if you're talking about 3D geometry, there are x, y, and z. So that is a vector with 3 dimensions. So the point x will have all the three points for 3 dimensions, and point x in 2 dimensions will have 2 points. So that x basically belongs to Rn. So all the real value numbers in all the n dimensions. So that is what it is conveying in here, right? Now next we will go on ahead and understand like what is matrices, right? So matrices are basically 2D array of numbers. So each element is identified by 2 indices. Since they are 2 dimensions, so these are 2 dimensions, every element is identified by 2 indices, one of row and one of column. So matrices is basically defined by a typeface, bold typeface. Basically it is A or B or C, or so any bold typeface is used to define to name a matrix, basically matrix. And elements in the matrices is indicated by italic but not bold. So all the elements in here, each element, these ones, are indicated by italic. And the element is basically it starts from the top left and then it goes down to the bottom right. That is how it goes. So we count from here as 1 1 1 2 2 1 and 2 2. So 1 is basically the row here, and 2 is basically the second 2 is basically the column 2 here. So this is 2 2. So the second number 2 is basically column, and here the second number 1 is basically the first column. So second number 2 is basically the second column. The second number 1 is basically the first column. First number 1 is basically the first row, and first number 2 is basically the second row. So that is how it is. So AI is the ith row of A. So when we talk about AI, such as I told you, like what is AI. So I is basically the row number. The first is IA is basically the row number, and IJ is basically the column number. So we write as AIJ, right? That is how it is represented in here. The next thing is that if A has a shape of M and width of N, the real values then belongs to R into M into N. So basically it belongs to a relation of real value elements which has a dimension of M into N. So M is basically height, and width is basically width is basically N. So you could understand this as a rectangle. So height could be your breadth and width could be your width. So width could be your width. So height could be your length and width could be your width, basically. So that is how it is represented. So it is a rectangle, right? So you could see that you could imagine this matrix as a square matrix because it has the same number of rows and same number of elements and rows and columns. So it is 2 by 2 matrices, right? Two cross 2 matrices. So basically, it is a square, right? So you can understand this, that this is the matrix in here, and it has it belongs to like R2 into 2. So basically, it has 4 elements. So R2 into M into N, basically it gives the total number of elements in a matrices. So that is how you understand what is a matrix is. Now, apart from matrices, we have something called tensors, right? We have something called tensors. So tensors is basically what tensors is. Tensors is multi-dimensional arrays, you could say. They are multi-dimensional arrays, as in an array which has more than 2 axes. So this matrix is basically an array with 2 axes, and if we go more than 2 axes, then we have a tensor, right? It has a 2 axes such as the first index is row and the second index is column. Now when we have one more such as depth, then we have a tensor. So that is what is the meaning of tensor. So it is a multi-dimensional array, right? That is what a tensor is. For example, RGB color image has 3 axes, right? It has 3 axes. It has length, it has breadth, and it has the third one. It is the color. So these are the three values of the tensor, of a single tensor. Right, a tensor is an array of numbers arranged in a regular grid with variable number of axes. Right, so the number of axes in tensor is variable. Axis here represents the axis of a dimension, right? So suppose if you consider a vector, it has if you consider a matrix, it has two axes. Now tensor has more than 2 axes. So that is how we understand what our axis is. Now we denote tensor with a bold typeface, same as a matrices. Now each element is like given like ijk. So suppose if the tensor is of 3 dimensions, so we denoted it with an ijk. So in here, the A could be represented as ijk, where ijk represents the length, the breadth, and the height points, right? This is a visual representation of basically tensor. So this is how a 0D tensor looks like, and this is the 1D tensor. So it only has one in one axis. It has only values in the one axis. When you go to a 2D tensor, it looks like a plane. It has values in two dimensions, right? So you could say that matrices is basically 2D tensor. Then we have 3D tensor, and then from the 3D tensor we have 4D tensors. Then 4D tensors, out of 4D tensors we have 5D tensors and 6D tensors. So if we stack 4D into if we stack 3D one over the other, we have the 4D tensor, and if we make a plane of 3D tensors, we have a 5D tensor, and if you make a cube of a 3D tensor, we have a 6D tensor. So this is how the tensors look like. There are much more representations in here, such as this one, such as if we are taking a column of tensors. Basically it is 1D tensors in here. It is 1D tensors in here, and it is like from top to bottom or bottom to top. So it is column of tensors, and if we arrange it in a 3D format, we get a third order tensor. It could be arranged in like row as well. It could be arranged as fibers or like tube as well. So these are basically fibers of a third order tensor. Third order tensor, as in it is in 3 dimensions. Now there is slices of third order tensors as well, in which we take the whole plane and not only the column. So basically we are taking matrices, two-dimensional matrices, and we are stacking over each other. That is basically the third order tensor. So one-dimensional tensor looks like a simple array. The two-dimensional tensor looks like a matrix, and three-dimensional tensor looks like something like this, which is basically like this if you understand in a pictorial representation, right? So this is basically we have to understand. There will be some doubts in this, such as what are these topics later on. We don't understand these things yet, but we will understand it, and we will go deep into this linear algebra as well, as in how it is going into vector notations and how this equation is representing a plane in a multidimensional space. We will understand this, so like we will go into the depth of this as well, right? So this is basically which is I'm going to cover in this right now, and after that we will going to go, let's see what is the next topic. We are going to jump into the Python, and we will just make some zero-dimensional, one-dimensional, and two-dimensional tensors in it and see how it performs, right? So we're going to do that in the next section, right? Okay, thank you. If you found this useful, if you have any doubts, you just ask in the comments and reply to me, and I will try to make you understand in a more in-depth way, right? Thank you.